Great. All right, can everybody see the slides okay? Yes. All right, sounds good. All right, so let's get started. So as Vivek said, my name is Ben Marlin. I'm a faculty member in computer science at UMass Amherst. Machine learning is my primary research area. I've worked in use-inspired research in mobile and clinical health, embedded systems, and IoT for the last 15 years or so since joining UMass. So the title for the first session this morning is LLMs Unplugged, Simplifying Generative AI for mHealth Innovation. So Vivek asked me to focus specifically on LLMs and its exemplar models. There's certainly lots of interest in this model class. So we'll talk about LLMs, we'll talk about generative AI, and their use cases and sort of capabilities and limitations. So just in terms of outline, I'll start with an introduction. I'm going to talk about some of the foundations for LLMs to get started. I know mHTI is always a mixed group, so people have different backgrounds coming in from different areas. So we'll give a brief introduction to what these models actually are, how they work, how they're trained. We'll talk about capabilities, so a level above sort of the mechanics of the models. What can you do with them? Some things you can do with them are very obvious, others are maybe a little bit more obscure. Then we'll home in on use cases in mobile health, and I'll go through some examples. There's lots of activity with LLMs and Gen AI in this space, in the clinical space as well, so I'm sure there are other use cases that people have in mind. And then I'll talk a little bit about issues and challenges as Vivek was describing. So this is still an area where the technology is still somewhat raw. It makes different kinds of mistakes. Trying to understand the failure modes and the relation to different kinds of regulations and requirements is something that's important. And then I'll give a brief summary at the end. So to jump in, at a very high level, in terms of some framing around how to think about AI, I think the popular press often conflates things like all of AI is machine learning or all of AI is LLMs at this point. So to give a little bit more of a concrete sort of foundation for how to think about AI, I really think about AI as a research area as a set of technologies that enable capabilities matching human intelligence. And so there are some core areas of AI research, like knowledge representation, reasoning, and planning, that you probably hear about less in the popular press, but are nonetheless very important. And then additional areas like learning, which encompasses various forms of machine learning, enabling different applications. So sort of large language models, pre-ChatGPT, going back 5 years or so, a large focus on machine learning in the health space was on problems that you can think of as perception applied to the health domain. So there's lots of activity using models like convolutional neural networks to do things like analysis of radiologic imaging, and there still are lots of applications in that domain. The more recent set of applications is in the synthesis space. So this is where sort of generative AI comes in applications that are not just doing recognition or detection or prediction, but that are enabling interesting generation of text in different modalities, including images and videos. And in the ML space, those models are also being applied to problems like time series data analysis and data generation. So an interesting component of some of the modern Gen AI methods is that they have both sort of an analytic and a generative mode, where you can use them to analyze, you can also use them to synthesize or generate. So we're going to work up to the point of thinking about some of the different applications that these technologies enable in the mHealth space, starting by going through some of the foundations for LLMs, so we can understand a little bit more about how they work, how they are trained, and sort of some of the affordances that they provide. So to jump into the core, I'm just going to give a sort of high-level definition for what an LLM or large language model actually is. So we think about these models as being supervised machine learning models with many parameters that accept text as input and that predict probability distributions over next tokens as output. Right, so this is specifically for large language models. There are other forms of foundation models that I think we'll hear about in the next section that are related, but that are not necessarily using language as their inputs or outputs. So I highlighted in orange on the slide a few different terms. These are sort of terms of art. We're going to break down the definition over the next couple of slides and look at what these different terms mean. So what is a supervised machine learning model? What does it mean to have many parameters? What are the parameters and how do they affect inputs and outputs? What does it mean to predict a probability distribution? What is a token? And so on. So some of these are, again, concepts that people may be familiar with if you have more background in machine learning. If not, you've probably heard things like token as a term of art, perhaps not clearly defined. So let's proceed through the breakdown. So I'll start just with this idea of a token. This is a sort of relatively straightforward idea. The basic premise here is that we could build models for text that operate at the word level. That's somewhat brittle, especially when you take into account the idea that you might need to represent or be able to generate names of arbitrary people or places or products and things like this. The list of possible words you might need to generate is very, very long. So millions of possible words if we think about generating text at the word level or analyzing text at the word level. So all a token is a subunit of a word. So a token can be as small as a single character. It's maybe more typically something like a syllable. It may be as large as an entire word. And there's particular technical reasons for doing this. It is a trade-off between the number of different possible options when you go to make a prediction for what's coming next in a sequence. For words, you have many, many more possible options. For tokens, you have many fewer. So standard tokenizers might have 100,000 different tokens. And the number of different items you need to generate. So if you're generating at the word level, you'll generate fewer items. Each item is sort of a larger semantic unit as a word. For a token, you might need to generate more tokens because each one is sort of a component of a word. So in terms of the way these models work, there's a favorable trade-off for having these sort of medium-sized semantic units instead of representing your data using whole words. So this notion of tokens is important to understand because it's tied to how commercial LLM providers charge for model use. So they charge for model use in terms of the number of tokens that you input and the number of tokens that the models output. So if you've worked with LLMs before, you've probably seen this per token pricing model. And this is what's going on. So if you give some text and you think about the number of words in it, that's not actually the number of tokens. And when you look at what comes back, again, the number of words is not the number of tokens. So the tokenization is a little bit hidden from you, but it's what's driving the cost of use of these models. Right. So in most of the rest of what I'm going to describe today, although models are using tokens sort of under the hood, behind the scenes, we'll use words as a sort of slightly more straightforward way to think about what the inputs and the outputs to these models are. Right. Okay. So in terms of how the models work, I mentioned the idea that LLMs take text as input and they produce text as output. That's the fundamental operation. So we'll look at a simple example here for what is the next word prediction task. The next word prediction task is the primary task that large language models actually perform. So they take an input that is a sentence, here again represented as words. They'll apply tokenization to break it up into individual tokens. At that point, the input as a sequence of tokens is fed into a model. These models are different forms of neural networks. The most prevalent architecture currently is called a transformer. Again, people may have heard that term previously. The architecture details for our purposes today are not going to be the most relevant. It's more the sort of overall flow of how these models operate. Yes, question? Oh, okay. All right. So we take our input, we provide it to our model, and then what comes out of the model is a probability distribution over the tokens. And here we'll just think about it as a probability distribution over the words. So these models are fundamentally probabilistic. They don't actually make predictions for the next, let's say, best word in a sequence. They produce a distribution over all possible words, or again, more accurately, all possible tokens, right? So the idea is the model is trying to just predict the next item in the sequence. So our input here is the capital of France is, and then the model's task is to output the most distribution over the next possible words, right? So on the right-hand side, you can see distribution over the dictionary. And here we have Paris being slightly more likely than some of the adjacent words, right? So if we want to make a hard prediction for a single item, there are different ways to take the distribution and decode it. The simplest thing to do is just predict the word that is the most likely from the distribution, right? So that's the fundamental operation that these models are performing. They take input sequences, they process them through a model, they produce a distribution over next items, and then sort of take a representative from that distribution. Again, typically doing something like the most likely item, although sometimes more complex forms of decoding. The next sort of layer here is the idea that the models are not static, right? They're parametric models, so they take as input the representation of the input sequence, as well as a set of parameters. And again, this goes back to the definition when I mentioned that these models have many parameters. We'll talk about what many means, but for now, we'll just talk about what parameters are. So the parameters are just numbers that characterize sort of and define the input-output relationship that these models have. The models aren't sort of hand specified in terms of the parameters. This is where machine learning comes in, right? So if you ask the question, how could we solve this task of learning to predict likely next words given particular input sequences? The answer is we'll appeal to the principle of learning as one of the foundational sort of components of intelligence. In particular, what supervised learning does is assume that we have a label available that is the correct output for a given input. Right, so here perhaps we have an input text in which we have the completion, the capital of France is Paris. So we have the input, we have the output for what the next token should be, or what the next word should be. The idea of supervised learning is that we'll compare the distribution that we generated from the model with the true label. We compare them using what's called a loss function. The loss function will take a smaller value, let's say when the distribution outputs a higher likelihood on the correct label, and it will output a larger value when there's a lower likelihood on the correct value, right? So this is a way of relating the model's predictions to the desired outputs. And then we use that signal to update the parameters, right? So the parameters are adjustable and we'll adjust them automatically. So this is the basic mechanism of supervised learning. It requires input-output pairs. It adjusts model parameters to decrease discrepancy or a loss function based on the model's current output and the desired output. So here, perhaps we change the parameters and we increase the probability that Paris is the correct answer, right? So the way that these models are trained, they're trained on many input-output pairs. You can see that, again, this notion of supervision requires a label, but if we're applying this mechanism to text, we have the labels, right? So if we have a text sequence, we can build an increasingly large window to use as the input. So imagine scanning through a sentence or scanning through a paragraph. We can use a prefix of text as the input, and we can use the next word as the output or the label. And so for that reason, these models are sometimes referred to as self-supervised. They don't need an extra human annotation for the label. The labels are coming from the sort of natural next item in an input sequence that continues beyond the cutoff point that you're currently using for the input. Right, so this is quite a flexible approach. You can use the same idea if you're trying to build models for video. You can look at a video sequence up to some point. You can use that as the input, and you could try to predict the next frame of the video and use that as the output. And that has the same sort of self-supervised kind of character. Right, so formally this is supervised learning, but because we're using it on sequences that are naturally labeled by the next items, self-supervised is another way of describing what these models are doing. So that's the notion of sort of the supervised learning piece, the probabilistic output piece, what the parameters are and what they're doing. They're controlling the input-output relationships, and we want to adjust them for better performance. In terms of generating sequences, how are the models used, right? So if we want to generate a whole sequence and not just the next word or the immediate next token, the models are applied in what's referred to as autoregressive mode. And so all this means is we take the output produced by the model at each time step and we append it to the previous input, creating a new expanded input, and then we run the model again. So again, simple example, we start off with the input sequence once upon. The model produces A as the most likely output. That most likely output is fed back into the model as part of the input at the next sequence position. So we have once upon A, and then the model generates time as the most likely next token or next word. So now we have once upon a time as the input in the third step, and the model generates there as the next output, right? So the models are not generating sort of in a single pass multi-token or multi-word sequences. They generate single words or single tokens at a time, and this autoregressive process is used to complete the sequence, right, or generate a longer sequence. So there are special tokens in the model that tell the model when to stop generating. So there'll be an end of sequence token that has some probability as well, along with the other tokens that correspond to parts of words. And when that token is generated, then the model will stop, let's say, anthropomorphically when it has finished its thought, let's say. Right? So you can see how these pieces sort of fit together. The base model is just trained on predicting the immediate next token. We can get it to generate much longer sequences in this autoregressive mode. Right? So that's the basic structure of how the model sort of is learned and how it's applied to accomplish this goal of sequence generation. Okay, so in terms of model sizes and this notion of large and large language models, the size of the model is sort of interpreted as the number of parameters the model contains. And so the table here just goes through several different models, sort of sorted in size order by the number of parameters, going back to GPT-2, which precedes ChatGPT from OpenAI. Original models in this space were sort of at the billions of parameters level. Current models like GPT-5 don't have full details available in terms of their architectures and number of parameters. So the items here annotated with a tilde are sort of approximations, sort of estimates of what the model sizes might look like. But you can see that current models are roughly 1,000 to 2,000 times larger than the models where this field started relatively few years ago. So most of the current models are estimated to have somewhere in the thousands of billions or trillions of parameters in the model that are all adjustable, right? So one of the important principles of supervised learning is if you want to learn a larger model, you need to have more available data. So if we think about the number of input-output pairs, that's an important consideration for how large the models can be. Right? So the next column in the table is indicating the number of training tokens used to train the models. And again, original data sets here were maybe at the 40 billion tokens level, and those would have been used sort of sliding window style as I described, where you use a sequence prefix as an input and use the next item as the output and then slide along. And current models are estimated to use somewhere between 40 billion and 100 billion training tokens. So these are very large models in terms of the number of adjustable parameters, and they're being trained on very large amounts of text input data. The last column on the table is sort of whether the parameters of the model are actually available to researchers or to practitioners to use directly, or whether the models are closed. So this is an important consideration, especially for people doing research in the health space, and we'll talk about this when we talk about regulation in more detail. But if you're running on, or if you want to run these models on text data or other inputs that contain protected health information, PHI, you can't do that in the standard sort of commercial APIs. They're not HIPAA compliant environments. So for versions of these models that are open weights, that means you can download a local copy of the model. And if you have appropriate compute hardware, you can run it locally. And in that case, you're controlling everything and you can sort of do whatever you like. You can put whatever data you want into it as long as you're in a sort of HIPAA compliant compute environment, which many hospital systems and university systems are constructing or have already constructed. So you can see that some of the larger models here are in fact open weights, like the DeepSeek model that released last year, but the largest models coming out of frontier labs like Anthropic, Google, and OpenAI are closed only. So some of them do have the ability to accommodate sort of HIPAA requirements, but setting that up can be quite cumbersome, especially for a small project. So we'll come back to some of the regulatory requirements a little bit later. Okay, so that's the large and large language models. In terms of training data sources, where is all this text data coming from? It's coming from the web. So effectively every book that's ever been scanned, papers that are available, legal briefs, patents, web pages, Wikipedia, Reddit, GitHub, Stack Overflow, Twitter, Instagram, all the text that you can think of that's available to these various companies that are constructing models is being used as part of the training sets. So the original sort of 40 billion set that was used by OpenAI was mostly a web crawl. Subsequently, different companies have been using whatever data they have available. Including, for example, XAI using data from X, formerly Twitter. All right, so that's where the data is coming from. And again, we'll talk about some of the legal implications of sort of consuming all of the data on the web as well. There's very open litigation around the ability to use these data and whether it actually falls under fair use or not. So I'll highlight that a little bit later as well. So hold on to that idea and we'll come back to it. In terms of the rest of the training sort of process for these models, a sort of raw large language model trained on the various text sources that I just described, using the next token prediction problem as I described it, The resulting model is very raw in a sense. It's really just trained to do this next token prediction task. It will not follow instructions that you give it in a very natural way, for example. And so for that reason, LLMs undergo a variety of kinds of post-training that are also designed to adapt the model parameters, but with slightly different goals in mind than just next token prediction. So this step uses different kinds of techniques. So there's an approach called supervised fine-tuning, where you train on human written prompt response pairs to get the model to better follow instructions or perform specific tasks. So your training data is just all kinds of different texts from lots of different sources. You may want to train it with particular additional goals in mind. So for example, if the user asks a question, you want to answer the question maybe accurately and succinctly. There are different kinds of requirements that you might think about imposing. So supervised fine-tuning is one way to accomplish this, where you give the model some examples of how you would like it to respond when a user provides a question, as opposed to just completing a particular input sequence. That process is quite high quality, but it's very expensive to generate example input-output pairs. A different way to use the models is an approach called preference optimization. This includes approaches like reinforcement learning from human feedback that people may have heard of. Here you have the model generate multiple outputs. So you generate the prompts or questions or obtain them from different sources. Have the model generate different outputs and then rate the outputs. So you could have a human assessor give a preference assessment for whether option A or option B is a better answer to a question or a better completion of a prompt. And you use that to re-optimize the model to get to better align with human preference judgments about what's more useful as an output from the model. And then there are other approaches that sort of fall into the post-training alignment around prompt engineering. So the first two, the supervised fine-tuning and preference optimization, these are approaches that are applied by the large language model providers. Once you're in front of a model like ChatGPT or Gemini, you can still manipulate how the model interprets your inputs using different prompt engineering strategies. And this has been very prominent in the sort of popular press over the last couple of years since ChatGPT came out. There are different strategies for manipulating the model just at the input level, where you can provide background information, give it different research papers to look at. This is called retrieval augmented generation. There are different strategies for prompting the model to go through different reasoning steps. It's often called chain of thought or COT to improve performance on your tasks. So this is a way of sort of input level post-training manipulating of the model to try to get it to be better aligned with what your particular goals are in terms of how you want to use the model. So depending on the level at which you can interact with the model, if you're running something locally and you can afford to fine-tune it, you can do some of these things yourself. If you're operating with a commercial API or you have a pre-trained model and you don't have data to fine-tune it, you can still influence the outputs at the prompt level. Okay, so that's a quick rundown of what the base models are, how they are created, how they operate, and then how they're sort of fine-tuned to provide the capabilities that we actually see. So we'll talk about some of the capabilities next. This post-training / alignment phase is very sort of important for actually surfacing the capabilities that are latent in the models based on just being trained to predict next token. So those capabilities are there, but they're not necessarily automatically surfaced without doing some of these additional sort of post-training modifications. All right, so I'm going to talk a little bit next about just straight capabilities, and then we'll relate this back to mHealth in the next section. And again, these are likely things that you've seen if you've been interacting with LLMs in different ways, either for research or for teaching or for other purposes. The general sort of workflow, getting something like ChatGPT to answer questions for you or Gemini is quite natural. So people are likely familiar with the idea that the models, the way that they are fine-tuned, particularly instruction-tuned, is to follow your instructions. So if you ask for the model to do something, like plan you a 7-day vacation in Los Angeles or something like that, the models understand after fine-tuning what you're asking. They will sort of pretty structured output to match the query that you gave, right? So the models have very high propensity for instruction following and sort of not going off task at this point when you ask them to do something. In terms of other capabilities that people have seen, generating fluent text in different styles, formats, and languages. People had a lot of fun with this a couple of years ago, getting models to generate in the style of Shakespeare or Dr. Seuss. I think that's run its course at this point, not particularly useful in an mHealth context, but the models have that capability. More importantly, they have the ability to translate between different languages. That's maybe a more practical use case as a sort of sequence-to-sequence style translation problem. They have the ability to recall information and answer questions. This is where things start to go off the rails a little bit with models. If you ask the question, where is the information that the model is using to answer questions stored? It's stored in the model parameters. That is a sort of lossy encoding of whatever that information actually is. The models have a propensity to make mistakes when answering questions because of the distillation of all of the text into the model parameters. And if you recall what that looked like, there's a gap between the amount of text data going into the models and the number of parameters in the models. The models can't just memorize all that text data, and furthermore, you wouldn't want them to in the first place. But that means they will occasionally recall information correctly. Incorrectly. They will answer questions incorrectly. They will generate outputs that are inaccurate for the particular query, right? So the models have this capability. It's quite compelling, but it's subject to inaccuracy and hallucination. We'll talk about that a little bit more further. The next thing that these models can do, as I mentioned, is operate in a analytic mode. So they can do things like understand and then manipulate text data to do things like summarization, which is quite helpful if you're looking at large volumes of text data. Again, you have to be a little bit careful. The propensity to hallucinate or generate incorrect outputs for summarization is somewhat less than for straight recall or question answering because you're giving a source document and it provides more structure for the model to latch onto. But there's still a potential issue there where the model can incorrectly summarize or hallucinate facts that were not present in the original text, particularly if the original text that you're asking to be summarized is in conflict with what the training data to the model look like. Okay. There are other capabilities that the models have that are quite interesting around what's called in-context learning. So you can effectively get the models to solve different kinds of input-output completion problems at the prompt level. This is often called in-context learning. It's an interesting way to solve sort of small supervised learning problems where you only have a few examples and you'd like to build a model. You'd like to have a model that can leverage lots of background information to solve the task. So LLMs are quite good at this sort of few example. This is called few-shot generalization in machine learning problem, where you just give a few input-output examples, and then you give the model a bunch of examples, and it will sort of complete the examples in a way that matches, or complete new examples in the way that matches what you provided as input. So I'll just give you a quick example of that. So this is ChatGPT. This is an example of few-shot generation based on something like product rating. So there's a few examples given in the prompt around product reviews and then corresponding ratings. And so you can see there's very little information given in the prompt. It just says, consider these examples, complete the last example. So the first one again reads amazing quality, the fabric is soft, it fits perfectly, highly recommend with a rating of 5, right? So there's a couple of examples of what this looks like. The last example says terrible product, didn't work out of the box, the instructions were confusing. And then the model completes the last example with a rating of 1, right? So if you wanted to look at a problem like this where you have a few examples but not a lot of examples and you don't want to go through the process of building a sort of a bespoke machine learning model for that task, this kind of in-context learning for specific tasks is something that these models can actually do quite well. It's an interesting capability. Okay, in terms of generative AI extensions, so large language models are a form of generative AI, but there are other forms of generative AI that are not about generating text. And so I'll just mention a few of them because they're likely relevant for different people. Summarization, like I mentioned, is something that's quite interesting as a capability, although again, you have to watch out for hallucination. Here, there are some interesting tools around sort of AI research assistants that can do things like summarize multiple sources, like a collection of research papers, research papers answer questions based on multiple sources. Google has a sort of demo product called Notebook LM that, if you haven't seen, is quite interesting. It will summarize a collection of research papers into a podcast that has different output sources to allow you to consume the information in different ways. So it's an interesting sort of system and set of capabilities. These models are also very good at code generation and editing. People may have heard about some of these models and products like Cursor, Claude Code, Codex, OpenClaw that are able to manipulate computer code at fairly large scales at this point. And again, there are issues with that as well in terms of accuracy and sort of the code version of hallucinations and inaccuracies. But a lot of these tools are proving to be quite useful. They've been integrated into a lot of software engineering workflows at this point. So that ability to sort of generate and edit code is something that's also quite well, and that's based on text prompts as well. So it's a text-to-text sort of sequence-to-sequence kind of capability, but it's a translation between user intent as described in text and computer code implementing whatever is described. Also on this list, I put in agentic models. I mentioned OpenClaw. People may have heard of OpenClaw earlier this year. These are models that are trained to autonomously leverage different kinds of tools. So, ChatGPT has a few things it can do now. It can search the web if you ask it to. It can use certain kinds of APIs. The more sort of fully agentic models can be hooked into sort of arbitrary websites. They can do all kinds of things for you. There's a lot of security concerns around agentic models and how much autonomy they have and what data sources and sort of resources people are giving them. There are interesting examples that came out over the winter, again, with the OpenClaw system, with it doing things like deleting people's whole code bases and things like that, which were quite unfortunate. But again, this issue of giving models lots of autonomy and limited oversight and access to actually important resources, that is fraught in the sense of the kinds of errors and their implications can be quite severe when things go wrong. They can be very useful when things go right, but there are higher stakes when things go wrong. Okay, so this one's just a quick example of code generation. So this is a quick prompt to generate a piece of code to do linear regression, reading in some data from a CSV file. Again, in Python, not a lot of code required, but again, this is sort of vibe code data analytics in some sense. And different kinds of tools are integrating this kind of capability. So a lot of the no-code platforms like Tableau and other similar sort of web-based systems have this ability now as well, where you can sort of give a prompt to an agent inside the piece of software, and it will create dashboards for you or do data analysis for you. So we're seeing the integration of these kinds of tools all over the place at this point, not just in the sort of browser-based LLM chat interfaces. But again, this kind of output can be quite good for very common tasks. If you're doing something quite bespoke or that no one has done before or that is not well represented in the training data, this can also go off the rails and either generate code that fails to run or that produces incorrect outputs. All right. In terms of other capabilities in the generative AI space, again, there's multimodal generative AI instead of just approaches that are related to text or code. And so this includes models that can do things like image to text. So the ability to understand images is something that has been important in computer vision for a long time. The current generation of models is able to generate text descriptions of the content of images, perform visual question answering. So you can provide an image and ask questions about it. Where is this, or what is this person doing in this image, and get answers back. So that's an analytic mode. You can do text to image, which is the reverse direction. So give a text prompt and get back an image. You can do text-based or prompt-based image editing. There are different approaches for that. So OpenAI has a model called DALL-E 3, which is what is integrated into ChatGPT. So if you ask ChatGPT to generate you an image, that's what's being used under the hood. Adobe has a model called Firefly, which is very similar in terms of supporting image editing, as well as just straight image generation. And text to video also exists. So here, these are models that can take a text prompt and then generate video. This is a capability that's been in the works for a number of years, along with image generation. These sort of text-to-image, text-to-video models just keep getting better and better in terms of their ability to generate sort of photorealistic outputs. They're still not perfect. This is a quick example from Sora last year. OpenAI released a new sort of social media site based around the second version of this text-to-video model. As sort of a social media platform. It was a bit of a weird offering, and I believe they're going to discontinue it this fall. So it seemed like it didn't quite hit in terms of a use case that lots of people were interested in using. I think it generated a lot of interest when it first released, but return users seemed a little bit more limited. Okay, so that's sort of common affordances for these models, things that you can do with them in general. I think the more interesting question for this group is, what can you do with them in mobile health? So how do these capabilities and affordances of models actually map into things that we might be interested in doing in the mobile health space? And then in the last section of the talk, we'll talk about issues and challenges. So I'm just going to run through a couple of things, and I'm going to sort of put some assessments on these in terms of how ready they are to use, given the challenges that I've sort of mentioned along the way. So a first use case might be something like health literacy, let's say health documentation literacy enhancement. So doing things like translating complex medical and technical language into plainer language is something that these models can do in a reasonable way. This is still something where you would obviously want to vet whatever comes out the other end of this process, but you could get significant simplifications. If you had if you had post-op care documentation, for example, and you wanted to rewrite it to accommodate maybe lower levels of literacy or be more generally accessible to people, make sure that you're removing more jargon in terms of art. This is something that the models can do quite well now. Again, with human vetting of the output, you need to be able to verify, but this is a reasonable example of an application. So this has potential to improve comprehension of consent documents, study protocols, instructions, and so on. So as a sort of English to English translation, but with a literacy level modification, this is a perfectly reasonable application of this kind of model. Another example that can be interesting to think about in the mHealth case is user simulations. I think you'll hear some about personas and persona modeling if you haven't already. LLMs are actually quite good at this, so you can prompt them with a persona description and then have the model operate in the mode of that persona and get it to give you feedback on different kinds of inputs. So again, with the ability to do image to text, you could provide different kinds of study materials, you could provide different kinds of intervention materials, and ask for feedback. So to the extent that the LLM understands the persona, the better the description is, the more it will sort of role play for you in that mode. And again, this is something where, as a first step before you go out to real participants and do something costly like bring people in for a focus group, this might help you work out some initial bugs in a reasonable way. Intervention content generation is another useful mode here. So leveraging the LLM sort of generation capability to give some examples of maybe concepts that you're interested in building intervention content around, and then examples of specific pieces of content that you have hand-tailored, and asking the model to generate different kinds of variations within particular bounds. This is another good application. So you could write a pool of 25 motivational messages, or look at different kinds of maybe image content, and then have the model generate an expanded set for you. And this is still something where the model has the capability to perform this task. You would still want to check it, especially if you're interested in alignment against particular behavioral constructs. So if you wanted a message that was consistent with particular behavioral theory, for example, you would still probably want to look at it and try to decide for yourself whether it expresses that construct in the way that you would like or not. But the models have the ability to reduce friction here by helping you with ideation effectively and generating lots of different examples. So you can just select among them, right? So another useful task. And yeah, the last note here is just that if you have particular theories you're interested in expressing during intervention content generation, you can provide detailed descriptions as additional supporting documents. That again, this notion of sort of RAG or in-context learning, just tell the model something about the domain and the concepts that you're interested in, will help it to generate more helpful outputs for you that will be of higher quality. Analyzing participant free text is another example. There are tools that do this already. You can use the sort of standard models for this as well. If you're interested in coding participant provided text, and you can give some examples or give instructions for what you like. Again, text maybe from in-study surveys or exit interviews. If you have them at high volume, this might be a reasonable way to get a quick look at what's going on in a bit more of a structured sense. Again, you have to be careful here that you're complying with HIPAA requirements. If there's the potential for participants to disclose PHI, don't run this through commercial sort of standard APIs that are not HIPAA compliant, of course. I mentioned automating programming tasks. So in mHealth, there's a large component around, often a large component around either web interfaces or mobile interfaces. You need to put sort of study apps in front of people or study websites. LLMs have the potential to help with this as sort of software engineering support, adding new basic features and things like that. The models are fairly good at, especially for the web. So because there's so much code available online, implementing different kinds of web interfaces. These models are very good at like prototyping interfaces for websites. They're very good at doing front-end development. They're less good at doing anything that has to do with security currently. So you probably wouldn't want to sort of use these kinds of approaches to build sort of participant login and data storage layer for you. But for prototyping interface ideas very rapidly, these tools are quite capable there. And again, there's more specialized offerings that are coming to light as well. There's lots definitely that you can do here. So I have the up arrow here is sort of emerging area as opposed to the check mark where these are basically good to go with verification. These ones are a little bit more, you have to be a little bit more careful with some kinds of program generation. The last one I'll mention here is something like a personalized health coach. And we're seeing this different proposals and research projects leveraging this idea in the mHealth space of basically using an LLM to provide personalized advice in areas like sleep, diet, exercise, hydration, stress, based on data from wearables and EMA responses, maybe participant goals. So the LLMs have the ability to sort of interpret this data and suggest different kinds of changes or interventions. The reason why I'm sort of marking this as sort of on the improve, but not maybe check mark that this is totally safe to do, is that there's still evidence of things going sort of badly off the rails with free interaction of individuals with LLM agents. And so whether you want to expose an app that does that to people is, that has that affordance for individuals, I think is still a little bit questionable in the space. So the possibility for hallucinated sort of incorrect advice to come out through this kind of interface directly to an individual, not from OpenAI, but mediated through your app as a researcher is something that I still think has sort of unacceptable levels of risk. All right, so that's a look at some specific applications and what their sort of risk profiles look like. The last thing I'm going to do is just cover some of the challenges, and I've mentioned a few of them along the way. We'll just dig down into some of them in a little bit more depth, including the ones that are a little bit more relevant and less discussed in health research. All right, so there are four main areas that I'm going to talk about here quickly. One around sort of hallucinations and alignment, including inaccuracies. One around environmental impact, items around legal issues for generative AI providers that are useful to be aware of if you're leveraging these services. And then the last one around regulatory issues for Gen AI users, specifically in the health space. And again, there are lots of issues in this space. We'll touch on a few. So the first I'll mention, again, this idea of hallucinations, I've mentioned a couple of times offhand. So this is just the idea that the model receives an input and produces an inaccurate output of some kind, perhaps hallucinating facts that aren't true, or simply providing inaccurate answers to questions. The broader issue of alignment is about whether the models sort of do what you ask or do what they are asked to do. There are interesting questions in AI safety in this part of the space about models maybe doing things like reward hacking, where they understand the overall objective and maybe try to shortcut to it in a way that skips important instrumental goals. So this is an example from a couple of years ago that people may recall, where when Gemini first went online, it was documented to do a number of strange things, including this example of telling people to eat rocks as an output to particular question. So again, like this is 2 years old. The models have improved 2 years since this. They're not doing things that are quite this egregious commonly, but there are still examples in the popular press, reports of sort of suicides linked to LLM use and sort of open use of chatbots, where conversations go completely off the rails in a very unhealthy way that's resulting in very adverse outcomes for people. So this is something that I'm sure everyone is aware of if you're sort of following the LLM space. The propensity for this kind of thing to happen seems to be rare, but it's not zero. So it's things to think about in terms of how the models are being deployed. In terms of environmental impact, again, this is hopefully something that people are aware of. I think there's increasing recognition of the environmental impact of generative AI. There's lots of stories in the news right now around data center development or sort of Gen AI data center development. The consumption of resources like electricity and water for cooling is quite high. There's lots of talk around stress on the sort of electrical generating capacity of local areas that are hosting data centers, as well as efforts of companies to develop, for example, micronuclear capabilities to power data centers. So the energy cost of running these parameters with thousands of billions, or models with thousands of billions of parameters is quite high. And that's putting some stress on a number of different resources. So again, when you're thinking about and contemplating the use of different kinds of models, the general guideline there, where models that have more parameters are generally using more resources, they'll generally cost you more as well. So there's already a sort of signal there maybe to select the model that is just powerful enough to accomplish the task that you're trying to perform, and maybe not more so. All right, in terms of legal issues, I would say the regulatory landscape for model providers right now is quite fluid. There's an active lawsuit by the New York Times against OpenAI for the use of New York Times articles as part of the training data set for ChatGPT. Model providers are claiming that this is fair use under US copyright law. The content creators and copyright holders disagree about this. And again, this suit, I think there was a motion to dismiss that was denied. This case is still going forward. There are similar cases against various image generators. I think Anthropic just settled the case this week or the week before. So things are quite fluid in the space. There's just generally a lack of sort of suitable legal frameworks. I think in the US as well, around sort of who can hold copyright. Only humans can hold copyright, so you can't actually copyright output from models either. So there's interesting challenges both on the sort of training side and on the generation side in terms of works that are supported by various kinds of AI models. So that's something to be aware of as well. There's sort of risk on the model provider side with respect to certain types of training procedures and training data collection strategies. All right, so the last one that I'll mention is regulatory issues for generative AI users, particularly the things that you should be concerned about coming at this from a health, sort of clinical or mobile health standpoint. So the first I'll mention is the most obvious, I've mentioned a couple of times, and this is the interaction between PHI, HIPAA, and using commercial LLM providers. And this one's very straightforward. There's no gray area here. You cannot sort of send PHI to a commercial API provider for an LLM if the environment that data are going into is not HIPAA compliant. And I've seen projects where people claim to do things like use one layer of an LLM to strip PHI before requests go to commercial vendors. That also, and with no human review, that's also quite problematic. I think the sort of use of guardrails there would need to be quite significant to make that approach actually feasible. If you are interested in interacting with LLMs and you have data that may have PHI in them, either sort of getting access to an institutional subscription for a HIPAA-compliant LLM environment, there are a few, or self-hosting open-weight models where you can, if that's a viable alternative, is a reasonable thing to do as well. So if you're doing things like generating intervention content or having models do text summarization, you don't have to worry, that's fine. As soon as you start thinking about inputting data generated by study participants directly into models, there you need to be careful with what you're doing to make sure you stay fully HIPAA compliant. All right, the last one here is about FDA. So Vivek asked me to touch on this one specifically. This is about upcoming regulatory requirements for software as a medical device that includes AI components. So in January of last year, the FDA issued draft guidance for AI-enabled software functions. This includes guidance for documentation requirements to support safety and effectiveness evaluations that will be performed by the FDA. So if anyone's thinking about transition of technologies that they're developing in the academic setting out into products, there are various FDA pipelines. This draft guidance is not finalized, but I think it's a very, it's likely that pieces of this that are described will stay in place. There's a 60-something page document that describes this in detail. I'll mention a couple of the items. FDA is picking up on ideas like model cards that have come out of the machine learning sort of safety community over the last number of years, but it's actually even more extensive in terms of the documentation that they're requiring. And it makes sense in terms of how they're thinking about the use of AI sort of included in devices. They focus on what they call a total product life cycle that includes how AI is designed, how it's used for pre-market submission, and then real-world monitoring and changes to systems sort of post-deployment. So I think for people who are working on building AI-enabled devices or AI-enabled software that might need FDA clearance at some point, understanding now what the documentation requirements might look like is important. And this is a distillation of sort of the ones that are most relevant for AI specifically. So there are basic questions around how AI is leveraged to achieve the device's intended use, architectural details like inputs, outputs, the architecture of the model used, and then data used for training and evaluation. How those data were collected in the first place is also part of the description. So this is quite a bit more detailed than what a standard model card would look like if you've seen one. Training methods used down to like what is the optimizer that you use, the use of pre-trained models in AI systems. What performance metrics did you look at? What performance assessments did you perform? And then broken down by particular protected subgroups is also something that the FDA is interested in seeing. So not just we got an AUC of 0.9, but this is how it did across different demographic subgroups that were captured in our data. They want to know about limitations from the data, from the model, or the device that you know about or that you've seen. They're interested in post-deployment performance monitoring approaches. So if you put this out in the field, how are you going to keep track of whether it's working? Is it drifting away from the performance it initially had over time? What does its performance characteristics look like under deployment as opposed to under development? There are a number of AI risk issues that they cover sort of under a cybersecurity heading involving how your model, when in the real world, will be resilient to things like poisoning, bias, evasion, overfitting, drift, as I mentioned, and so on. So again, these are like topics that have been around for a while in the machine learning community. There is active research on these. We encourage people again to like have a look at some of these items if you're thinking about moving towards this pathway, because I think there's lots of work that could be done preemptively or prospectively to collect this information as you go. If you had to go back and reconstruct some of this post-hoc, it might be a little bit challenging or painful. And again, this document that I'm summarizing on 2 slides is 60-something pages long. So if you're interested in this topic, definitely search out that document and have a look at it in some more detail. Okay, so as we come up on the end of our time here for the session, let me just summarize with some key takeaways for you. There's a lot of information. So on the foundations, as I described, LLMs are pre-trained as probabilistic supervised models on the task of next token prediction. We talked about what supervised meant. We talked about what tokens meant. Current LLMs use hundreds of billions to trillions of parameters, and they're pre-trained on trillions to hundreds of trillions of tokens of text data. This is where the large comes from in LLM. For models to be useful to end users, they're post-trained using multiple approaches to improve alignment, so that notion of sort of various forms of fine-tuning. In terms of capabilities and use cases, LLMs have extensive capabilities, including text analysis, summarization, translation, and generation. Multimodal generative AI can analyze and generate images, video, code, and more. LLMs and generative AI have many potential applications in mHealth, but not all are safe to deploy currently due to some of the issues that I was mentioning. Right. So in terms of challenges, we still have problems with hallucinations, inaccuracies, and poor alignment for various Gen AI methods, and the implications of those will be more or less severe depending on the applications that you're considering. Researchers should be aware of the environmental impact of Gen AI use in their work. And again, that general idea of if you're going to use these models, try to use the least the model with the least environmental impact is a reasonably conscientious thing to do. Lastly, while use restrictions implied by regulations like HIPAA are clear, the overall legal and regulatory environment around Gen AI remains quite fluid. So there are open lawsuits in multiple areas that could affect the ability of model providers to continue to provide models in the way that they are. And it will take some time for that to shake out. The sort of federal and state level legal frameworks are also quite fluid. The previous administration released guidance, which was canceled by the current administration, which has then released some updated guidance in terms of just general frameworks for use of AI. So I think for the time being, we should expect the legal and regulatory framework in this space to continue to exhibit fairly high levels of uncertainty. Right. So, or just the time, I will end there. Vivek, I don't know if we have time to take a couple of questions. If not, if anyone has questions about things, I'm happy to get email from folks while you're working through your projects with mHTI over the summer. If there's anything I can help people out with, although I'm not formally a mentor this year, don't hesitate to reach out if there's something I can help you with.
Thank you. You covered the whole landscape and made it accessible in a very wonderful manner. I will take a couple of questions from the scholars. Anyone have questions? But we also appreciate your willingness. Okay, did I see a hand someplace?
I have a quick question, if that's okay.
Yeah.
So you mentioned some of the models if we're interested in using the AI with HIPAA data. If sort of our institution doesn't provide a license for that, what are some of the resources that are available? You think you said like building your own, or yeah, if you kind of provide more detail about that.
Yeah, there are a few different approaches. So there are some sort of API resellers that you can find. So if you do a quick Google search for HIPAA compliant LLM, there are a few companies that sort of buy HIPAA enclaved versions of ChatGPT, for example, or different OpenAI models, and then resell them. OpenAI, in theory, will enter into a contract with for an individual research project where they will give you access. I guess you have to become a business sort of OpenAI business partner, and they will give you access to the HIPAA compliant enclave. If you look at their website, they talk about the process for doing that, but for a while they were not processing further requests. So although it's there and it's something that it looked like you could do, it was not actually practically realizable. So the sort of third-party resellers that have already established the relationship to provide HIPAA compliant access would be one option. And then the other option, again, depending on resources, you can set up your own local models. You still need to have a HIPAA compliant compute architecture, sort of infrastructure to do that. So if you don't have sort of HIPAA compliant ChatGPT specifically, if you're able to run models locally in a HIPAA compliant sort of compute platform cluster or sort of data center that your institution runs. And again, this is it's relatively common for hospital systems to have this now, or academic medical centers. You can potentially run models there. They may have models already set up that you could use. So in the slide that I was giving The more advanced models that are open weights right now are models like the Llama model family. So these are models from Facebook that they've released as sort of open source. The weights are public. You can run the models locally on your own compute resources inside your own HIPAA compliant sort of data enclave. And there they have no interaction with the internet at all. The model's running locally. You can use it just like you would use ChatGPT, but it's running on your own computers, right? So you completely control everything, the data in, the data out. Nothing's leaving your enclave. So you're fully compliant. Those models are somewhat less powerful than something like GPT-5.